Hi everyone, welcome to lesson 3 today of our exponents and logs unit. Today we're going to be working with solving exponential equations. Before we get there, we're going to start on our opener question though, just to remind us of what happened last lesson. So we have a point 3, 125 lying on the function y equals 5 of x. If the transformation y equals of this function is applied to the original function, the new point will be what? So what we need to do here is, of course, mapping. So let's rewrite our new function here so that it's in proper mapping notation. First thing I noticed, I don't have a dedicated b value. I'm going to rewrite and isolate for a b value. So I have y equals negative 3 over 5x f of, and here I'm going to have 3x. So 3 times x gets me to 3x, and 3 times positive 4 gets me back to that 12 there. Minus 6 at the end. Perfect. From here I can go straight into my mapping notation. So I have 1/3 x minus 4 comma negative 3 over 5y minus 6, and there we go. From here I'm just going to sub in my values for 3 and 125 for x and y respectively. And that should get me negative 3 and negative 81. There we go. So that's our new coordinate. State the domain, range, and equation of the state the domain, range, and the equation of the horizontal asymptote of the new function. So if you had graphed this out here, so instead of graphing out just this, we know our base is going to be 5. So let's rewrite our new function. Let's call it g of x there. So this is going to be equal to negative 3 over 5, and this is what you kind of want to graph on your calculator. Negative 3 over 5 bracket 5 is your base. Exponent is going to be this 3x plus 4, and after all that, minus 6. There we go. So for this graph here, it's going to look like the following on our graphing calculator. So here I have my graphing calculator pulled up, I have my equation typed in, and I hit graph, and that's what my graph is going to look like. It's just going to kind of bend down there. So we have our domain here. Domain is going to be negative infinity to positive infinity because it's going as far left and right as possible, so negative infinity to positive infinity. Our range is, well, it's going to go as low as negative infinity, as high as this line here. This line so happens to be at negative 6, and if you drew in a line at y2 of negative 6, and there we go. So it's going to be at negative 6. So we have a range from negative infinity all the way up to negative 6, but because negative 6 is a horizontal asymptote, I have to use a rounded bracket, and of course horizontal asymptote at y equals negative 6. There we go. Here is the quick review of our exponent laws. Some of this you've learned previously, some of this might be new. But here it says if you have the common bases b and b, and you're multiplying and your function is multiplying, and you have two exponents, what are you really doing? This is just going to be bn plus m, so you're going to add them up. For division, it's going to be bn minus m, so you're subtracting when it's dividing. When you have an exponent to another exponent, it's going to be multiplying. So my multiplication, I just write my two variables beside each other. I don't use the x anymore in between them, just because x could denote a variable. And of course, b exponent 0 is always equal to 1. There we go. In this one here, we need to distribute this m into the brackets. Both of these have an exponent 1 on them, so we're multiplying each of these exponent 1s by that m there. So I have a exponent m and b exponent m. Same idea down here with the division, 1 and 1 on both of my numbers there, of both my variables there. So I have a exponent m all divided by b exponent m, as again you multiplied 1 times m. Here you never want to leave a radical, so what we want to do is rewrite it into fractional exponents. So this is going to be m divided by n. I'm going to put a star next to this one. This one was from 10c. And again, down here, anything exponent 0 is always 1. Over here, if you have a negative exponent, you always want to get rid of it by reciprocating. So you have a to the positive x. Down here, if it was already negative, you want to reciprocate to your numerator. So this is a to the positive x, and you don't have a 1 anymore there. And there you go. It's all a numerator. Here, if you have a fraction, the quick and easy way to do it is reciprocate your fraction and multiply in that x. So now we're going to have b to the exponent x over a exponent x. And last but not least, here our answer is -1 this time instead of 1 and 1. How did we do this one? This one here was negative of b exponent 0, which you had to evaluate first, which is 1, and then multiplied by negative to get you to that -1 there. And hopefully that quick refresher wasn't too tough. Up next, we're going to do something where we have to rewrite all these numbers with a common base, and so it's going to be the base that's indicated. So it says rewrite each with the indicated base. 8 with a base of 2, so that means you want to rewrite everything with base 2 and an exponent. So you're really trying to fill in this equation y equals c of x, and in this case here, this first one here, we have y being 8 equals c being 2, and x is right here, and you're wanting to find out what x value would get you to 8 there. And of course we know 2 cubed should get you to 8. And there we go. Is there a fast way to check this? Yes, of course, we can always use our graphing calculator. So on my graphing calculator, here's what I set up. I have base 2 exponent x, base 3 exponent x, 4 and 5 respectively. Whatever base you really need, you could just fill in, and all of them will always be to exponent x. I don't really need to graph this, as more so I need to see what it looks like on the table of values. So I'm going to pull up my table of values, and again, reminder, this is base 2, 3, 4, and 5 respectively. And how would you know? Always look at x equals 1, and that will tell you your base. So if we were looking for base 2, which is this first column here, and we had an answer of 8, which is right here, our x value had to be 3. And using our graphing calculator, of course, we double checked, so 2 cubed is always equal to 3 anyways. So that's the first one here. For the second one, we have 1 over 27. So in terms of base 3, we're trying to get 27 into some sort of exponent 3. So again, my base 3 will be my second column. 27 is right here. It's going to be x equals 3. So I have base 3 cubed. There we go. So 1 over 27 is the same thing as 1 over 3 cubed. The other way we could technically write this, by the way, is 3 to the negative 3. But again, if you have a negative exponent, you're always trying to rewrite it in this format here where you have no negative exponents. Over here, if you have 64x, or 64 exponent x with base 2, again, I'm going to go to my graphing calculator, look for 64. 64 again under base 2 is this first column. I have 6 for x with 64 there. So let's quickly rewrite this. Instead of saying 64, I'm going to say 2 exponent 6, and we have that x right there. And of course, I'm going to multiply that x with the 6, so now I have 2 to the exponent of 6x, and there we go. Over here, we have two different numbers, but again, we're indicating that we want base 2. So under base 2, I'm going to look for 16 and 32. So under base 2, I see 16 is going to be exponent 4, and 32 is exponent 5 of base 2. So for 16, I'm going to quickly rewrite this one first. So this one here will be 2 exponent 4, that's the 16, and I'm going to have that 1/4 right around it still on the outside. Over here, square root 32, 32 I know is 2 base 2 as my base with 5 as my exponent, radical sign right around it, and there we go, closing that bracket off. Here, let's do some quick multiplying. So if I have 4 times 1/4, this is now just 2 to the exponent 1, or just 2, however you want to write it. I'm just going to keep the 1 there for now. And over here, again, we don't want the radical, we want to convert it, so this is now 2 to the 5 halves. And again, where did this halves come from? By default, our index here is always a 2, so that 2 is now my denominator. And again, here, if I have a multiplication symbol, this really means I'm adding my exponents. So on my calculator, I'm going to go 1 plus 5 halves, or this is really 5 halves plus 2 over 2. So now I'm at 7 halves. And there we go. That's D. And for E, we're looking for 125, 25, all in base 5. So let's double check base 5s. Over here, last column, again, I'm looking at x equals 1 to find my base. I have 25, and 125 is 5 squared and 5 cubed respectively. So here, I'm going to rewrite this one as 1 over 5 cubed, because that's what 125 is. All of this still has that 3x plus 2 as an exponent, and over here we have 25, which is 5 squared, and all of that has minus 5x as an exponent. Here, I could work with this right away, but I'm just going to convert this into a negative exponent because I have 5 negative 3, and I'm going to have my 3x plus 2 there. Basically, I'm getting rid of that fraction. And over here, I'm just going to multiply out, so this is now 5 to the negative 10x over here. Down here, let's continue to simplify. So we have 5 to the negative 9x minus 6. And of course, we already had this 5 to the negative 10x. And of course, what do we do once we have common bases and we're multiplying? We're really just adding. So let's add up our exponents. And so this gets us to base 5 to the negative 19x minus 6. And so that's e there. For f, we want to rewrite everything in terms of base 3, and look here, we already have everything in terms of base 3, so all we have to do is evaluate our exponents here. So I'm just going to do a quick subtraction and see what we get. So here I have 3 to the 5t minus 1, and this is going to be subtracted by this 2t minus 6, which should be in brackets. I need to distribute out that bracket, and I end up with minus 2t plus 6, and collecting like terms, I end off my equation with base 3. This is now going to be 3t and positive 5, and there we go. That's the last question here. In the next example here, we're trying to solve our exponents, solve for x here algebraically. So here it says variable in the exponent. So what do we want to do? Well, we want to follow a few things. So the very first thing we want to do, and this is some quick notes that you may or may not want to copy down, but you want to, 1, change each term to a common base. That would be step 1. Step 2, you want to equate the exponents, aka make the exponents equal to each other. And step 3, you're going to solve for x. And there we go. 3 easy steps to try to follow, and we should be able to solve these questions. So here, if I see the number 9 and 27, I don't know what base might have 9 and 27, but I'm going to go to my graphing calculator. I'm going to look through all of my bases. So this is, again, base 2, 3, 4, 5. I'm looking for one of them that has 9 and 27. Right here, we have 9 and 27, so I'm going to convert everything to base 3. So I start off this question by rewriting it as base 3 squared, that's 9 now, and I have this 2x minus 5 on the outside still. 27 I know is going to be 3 cubed, and I have that x minus 2 on the outside. From here I can either I should distribute out my exponents, so this is now 3 to the 4x minus 10 is equal to 3 to the 3x minus 6, and there we go. From here, now that I have common bases, I can drop my bases and equate my exponents to each other. So I have 4x minus 10 equals 3x minus 6, and again I was able to do that because I have common bases that I can drop. Here I'm going to collect like terms, so I have x over here is equal to positive 4 over here because I moved the 10 to the right, and that's going to be my answer. In this next question here, again, I'm looking at 8 and 32. Again, I want to find a common base for them. 8 and 32 seem to be base 2. I have 2 cubed and 2 exponent 5, so here we go. So 8 is now going to be 2 cubed to the exponent x equals 2 exponent 5 there for 32, x minus 4. Again, multiply out, so we have 2 to the 3x equals 2 base 2, 5x minus 20. And again, I can drop my bases, so I have 3x equals 5x minus 20. And I want to isolate for x here, so I'm going to move my x, this is all to the left and leaving my numbers. So I have minus 2x here on the left equals minus 20 here on the right, dividing both sides by negative 2, x equals positive 10. On this equation here, I'm looking for 16 and 64. I see 16 and 64 right here in base 2, but I also see 16 and 64 here in base 4. I can use either answers and they should net me the same result. This one here, you're just working with a slightly bigger base, your base 4, here base 2. By convention, we usually use a smaller base, so I'm just going to stick to base 2 on this one here. If you did it with base 4, you'll get the exact same answer, by the way. So base 2, 16 is going to be 2 exponent 4 to the x minus 4 there, equals 64, which is 2 exponent 6 to the 2x plus 1. Again, multiplying and dropping my bases. If I multiply out, I get 4x minus 16, and I can drop my bases because they were both 2 and 2. And over here I have 12x plus 6. I want to move all my numbers to one side, so I'm going to move all my variables to the right this time. So I have 8x right here. Move my numbers to the left, that's minus 22. Dividing everything by 8, so x has to equal negative 22 over 8, which reduces down to negative 11 over 4. So that's B. In example C, again we want to find common base. So here, for example C, I'm looking for something with 36 and 216. Well, 36 is nowhere to be found on these, so most likely I'm going to need my next base. So if I have 2, 3, 4, 5, the next one I'm going to check is base 6. Second graph. Again, I don't see my base 6 here. I see 2, 3, 4, 5, but if you scroll to the right, there you go. You have base 6 come up. 36 is right here, so it's, of course, 6 squared. And the other number we were looking for was 216, which is 6 cubed. To rewrite this, let's see what we get. So I know that 1 over 36 is going to be 6 squared, and if it's in the denominator, I'm going to quickly rewrite it as 6 to the negative 2. That's my left, and on my right I got 6 cubed to the minus 2x plus 4. Distributing out my exponents and dropping my bases at the same time, I end up with positive 6x plus 4 here on the left equals minus 6x plus 12 here on the right. Combining my variables, I'm going to move everything to the left, so that's 12x, and moving my numbers all to the right, that's just 8. So x is now equal to 8 over 12, which should be reduced down to 2 over 3. On this example here, I'm looking for base 2, 125, and 1250. Well, first off, there's nothing in base 2 that will get you to 125. So if you look at base 2, the closest we got was 128. There is no 125 there. So what should I do? So instead of converting it to a base 2 right away, I'm going to divide both sides by 2. So I'm going to divide all of the left by 2 and all of the right by 2. Essentially this cancels and this cancels out. So I'm left with 125 to the exponent of 2x minus 1 is equal to 625 left over. From here, I'm going to look for something that has 125 and 625, and of course that's going to be base 5 with 5 cubed and 5 exponent 4. So here we have 5 cubed, 2x minus 1, and over here this is 5 exponent 4. Again, I can drop my bases, so this is now 6x minus 3 equals 4. And combining like terms, I have 6x equals 7, so x equals 7/6. Down here, for example, E, I see 4, 8, 2, and 32. as 2 is my smallest number there, most likely that's going to be my base, so let's double check base 2. So for base 2, I see 4, 8, 2, of course, and the other one we're looking for was 32. So let's rewrite example E all in terms of base 2. So here, this is going to be 2 squared multiplied by that x plus 1. The next term would have been 2 cubed multiplied by that x there. You have the equal sign. 2 there by itself is just going to be 2 exponent 1. I'm just going to leave that there as 2 exponent 1. Over here, 32 is the same thing as 2 exponent 5. And of course, we have that x there. Let's multiply out. So here we have 2 to the 2x plus 2. Over here, you have 2 to the 3x. Equal signs right here, that's 2 exponent 1, and over here it's 2 to the 5x. Well, in between all of these it's multiplication, so let's add these up. So here on the left I have 2 to the 5x plus 2. On the right I have 2 to the 5x plus 1. I can drop my bases as I have common bases, so now I have 5x plus 2 equals 5x plus 1. Combining all my variables all to the left, that's 0x's equals negative 1. This cannot occur. This does not actually happen. So therefore, on this one, we have no solution.